Hello viewers, in today's session we are going to discuss another important problem from differentiability of functions. So in this class we are going to discuss the differentiability of this function f of x at this point x is equal to 0, where f of x is defined as x times tan inverse of 1 over x, where x is not equal to 0 and f of x is equal to 0 when x is equal to 0, right? So here we have to see whether this function f of x is differentiable at this point x is equal to 0 or not. So for testing the differentiability of a function at a given point, we have to find out the right hand derivative and the left hand derivative, right? So here we'll see how we'll find the right hand derivative and left hand derivative using the concept of limits. So let us start. Now suppose we have a function, say y is equal to f of x, which is defined in some domain D, and suppose we wish to test the differentiability of the function at some point x is equal to a belonging to this domain D. Then we have to find out the right hand derivative and the left hand derivative. Now, if the right hand derivative and the left hand derivative both exist and they are finite and they are equal to each other at x is equal to a, then we can claim that the function is differentiable, right? So the condition for the existence of derivative of a function at some given point, the right hand derivative and the left hand derivative must be equal to each other, right? So let us here find out the right hand derivative and the left hand derivative of this function at x is equal to 0, and let us see whether both these derivatives are equal to each other or not. So now the right hand derivative is defined by this limit, that is limit, here we have h tends to 0 and f of a plus h minus f of a divided by h. So this limit gives us the right hand derivative, and the notation for the right hand derivative is given by f prime, and here we write a and here we put a positive sign, right? So this limit is it gives us the right hand derivative. So in this case the value of a is 0, so a is equal to 0, and here the function f of x is defined as x times tan inverse 1 over x for all x not equal to 0, but for x is equal to 0 we have f of x is equal to 0. So when x is equal to 0, f of x is given as 0, so this implies that f of 0 is equal to 0, right? So the value of the function at x is equal to 0 is equal to 0. So now we have a limit h tends to 0, and the value of a is 0. So here we have 0 plus h, and here we have f of 0 divided by h, and here we have f prime of 0, and here we have a positive sign, right? So let us evaluate this limit. So we have limit h tends to 0, this is f of h, 0 plus h is h, f of 0 is 0, because here f of x is equal to 0 for x is equal to 0, and here we have h. So now we have a limit h tends to 0, f of h over h, right? Okay, now we have to evaluate this limit. So let us find out the value of f of h by replacing x by h. So we have here h, then we have tan inverse 1 over h, and here we have h, right? So f of h is obtained by replacing x by h in this function. So now we have this h and this h get cancelled. We have limit h tends to 0, and here we have tan inverse 1 over h. So now we have to evaluate this limit. Now see here h is tending to 0. So when h tends to 0, then 1 over h, 1 over h tends to infinity. So here this limit is now equal to tan inverse infinity, because when h tends to 0, 1 over h tends to infinity. So now this limit is equal to tan inverse infinity, and we know that tan pi by 2 is not defined, that is infinity. So we can now replace tan inverse infinity by pi by 2. So here we have pi over 2. So the right hand derivative of this function at x is equal to 0 is equal to pi by 2. So here we'll write the right hand derivative equal to pi by 2. So let us now find out the value of left hand derivative. Now the left hand derivative is defined by this limit, that is limit h tends to 0. Here we have f of a minus h minus f of a divided by minus h, and here we write f prime, and here we have a and we put a negative sign over a, right? So this limit gives us the left hand derivative. So here the value of a is 0. So we have now a limit h tends to 0, f of 0 minus h minus f of 0 divided by minus h. So this is limit h tends to 0, and we have f of minus h. 0 minus h is minus h. F of 0 is 0, and here we have minus h. So this is limit h tends to 0, f of minus h over minus h. So now we have to evaluate this limit. Now to get the expression for f of minus h, we have to replace this x by minus h in this expression, right? So we have limit h tends to 0, and we have here minus h. For x we have minus h, and then we have tan inverse 1 over minus h, and in the denominator we have minus h. So now this minus h and this minus h get cancelled. We have limit h tends to 0, and we have tan inverse of minus 1 over h. So now from inverse trigonometric functions, we know that tan inverse of minus theta is equal to minus tan inverse theta. So here for theta we have 1 over h. So we can now write the left hand derivative is equal to limit h tends to 0, and we have minus tan inverse 1 over h, right? So tan inverse minus theta is equal to minus tan inverse theta. So now, as we have discussed earlier, when we have calculated the value of right hand derivative, when h tends to 0, then 1 over h tends to infinity, right? And we have now here we can write this negative sign in front of limit notation. So we have limit h tends to 0, tan inverse 1 over h. So now we have minus tan inverse, and here we have infinity, right? And tan inverse infinity is pi by 2, so we have minus pi by 2. So the value of left hand derivative is equal to minus pi by 2. So viewers, we have obtained the value of right hand derivative as pi by 2 and left hand derivative equal to minus pi by 2. And from this discussion, we see that the right hand derivative and left hand derivative are not equal to each other. That is, pi by 2 is not equal to minus pi by 2, right? So here, although the right hand derivative and left hand derivative both exist and they are finite when x is equal to 0, but these two derivatives are not equal to each other. Hence, we can claim that this function is not differentiable at x is equal to 0, because for differentiability of a function, both these derivatives must be equal to each other. So finally we can say that this function f of x, that is equal to x times tan inverse 1 over x when x is not equal to 0, and f of x is equal to 0 when x is equal to 0, is not differentiable at x is equal to 0. Hello viewers, in today's session we are going to discuss an important problem from continuity of functions, and in this session we are going to discuss the continuity of the function f of x, that is equal to 2 times greatest integer of x divided by 3x minus greatest integer of x, and we have to discuss the continuity of this function at x is equal to minus half. So now to check the continuity of this function at x is equal to minus half, what we have to do, we have to find the right hand limit of this function at this point, that is x is equal to minus half, and then we'll find the left hand limit, and then we'll find out the value of this function at this point, that is minus half. And if these three quantities are equal to each other, then we can claim that this function f of x is continuous at x is equal to minus half, right? So what we will do, we'll first find out the right hand limit at this point, then we'll find the left hand limit, and then we'll calculate the value of f of minus half. So let us start. So now the right hand limit is given by this notation, that is limit x tends to minus half, and here we put a positive sign, and here we have f of x, right? So now to calculate the right hand limit, let us make this substitution, that is x is equal to minus half plus h, where this h is infinitesimally very small, and it lies between 0 and 1, right? So the value of h is very small, and it lies between 0 and 1. So when x tends to minus half, then h tends to 0. So we can now express this limit in terms of h. So we have limit h tends to 0 for x tends to minus half plus, and here we have f of x, and x can be replaced by minus half plus h, right? Okay, so now let us write the value of f of minus half plus h by replacing x by minus half plus h in this function. So we have 2 times, here we have minus half plus h, and then we have 3 times minus half plus h, and here we have greatest integer of minus half plus h. So now we have to find out, or we have to compute this limit, and here we have the greatest integer of minus half plus h. So now let us find out the value of this expression, that is greatest integer of minus half plus h. So we can write this expression as minus 1 plus 2h over 2, or we can write here greatest integer of 2h minus 1 over 2. So now let us find out the value of greatest integer of 2h minus 1 over 2. And here we know that this quantity h is a positive quantity, and this h is it lies between 0 and 1. So when h lies between 0 and 1 and h is infinitesimally very small, then the value of 2 times of h should also lie between 0 and 1, because here we have 2h, right? So h is infinitesimally very small and it lies between 0 and 1. So the product of 2 and h should also lie between 0 and 1, and 2h is also infinitesimally very small. So now let us subtract 1. So we have 0 minus 1, here we have 2h minus 1, here we have 1 minus 1. So we have minus 1, 2h minus 1, and this is 0. And let us divide throughout by 2. We have minus half, then we have 2h minus 1 over 2, and here we have 0 over 2. So now we can write minus half, then we have 2h minus 1 over 2, and here we have 0. So from this inequality we can conclude that 2h minus 1 divided by 2, it lies between minus half and 0, right? So here we have 0 and here we have minus 1. So minus half, it lies somewhere here. So the value of 2h minus 1 over 2, it lies somewhere between minus half and 0. So the greatest integer of 2h minus 1 over 2 should be equal to minus 1. So the value of greatest integer of 2h minus 1 over 2 is equal to minus 1 by definition of greatest integer function. So now we can easily compute the value of this limit. So we have limit h tends to 0, and we have 2 times greatest integer of minus half plus h, and that is equal to minus 1. So here we have minus 1, and here we have minus 3 over 2 plus 3h, and for this we have minus 1. The value of greatest integer of minus half plus h is minus 1. So now we have limit h tends to 0. This is minus 2, and here we have minus 3 by 2 plus 3h and plus 1. So now when we take h tending to 0, this term is 0. So we have minus 2 minus 3 by 2 plus 3 times 0 plus 1. So this is minus 2, and minus 3 by 2 plus 1. So minus 2 over minus 3 plus 2 is minus 1 over 2, right? So minus and minus get cancelled, so we have 2 times 2 over 1, that is equal to 4. So the right hand limit of this function is equal to 4. Let us now calculate the value of left hand limit. So now the left hand limit can be written as limit, and here we have x tends to minus half, and here we put a negative sign, and here we have f of x. So let us substitute x is equal to minus half minus h to get the value of left hand limit, and when x tends to minus half, then h tends to 0. So now we have limit, and we can express this limit in terms of h, and here we have h tends to 0, and f of x is minus half minus h, right? And again this quantity h is infinitesimally very small, and h lies between 0 and 1. So now this limit is limit h tends to 0, f of minus half minus h, can be obtained by replacing x by minus half minus h. So we have 2 times minus half minus h, and then we have 3 times here minus half minus h, and then greatest integer of minus half and minus h. So now let us find out the value of greatest integer of minus half minus h, right? Because here we cannot directly substitute h is equal to 0. So to get the value of greatest integer of minus half minus h, we can now write it as minus 1 minus 2h over 2, and here we have minus, and we can write 2h plus 1 over 2. So now to get the value of this expression, let us again start with this inequality. So h is very small, infinitesimally very small. H lies between 0 and 1. So the value of 2h, that is 2 times of h, should also lie between 0 and 1. So now adding 1 throughout, we have 0 plus 1, 2h plus 1. Here we have 1 plus 1. So this is 1, 2h plus 1. This is 2, right? And let us divide throughout by 2. We have half. Here we have 2h plus 1 over 2. And here 2 over 2 is 1, right? So we have 2h plus 1 over 2. It lies between half and 1, that is greater than half but less than 1. So if we multiply throughout by minus 1, then we have minus half, we have minus 2h plus 1 over 2, and here we have minus 1, and the direction of the inequality get reversed, right? So now from this inequality we conclude that here we have minus half, and this quantity minus 2h plus 1 over 2, it is greater than minus 1 but less than minus half, right? So this value, that is minus 2h plus 1 over 2, is greater than minus 1 but less than minus half. It lies somewhere between minus 1 and minus half. So the greatest integer of this quantity should be equal to minus 1, right, from the definition of greatest integer function. So now we can write this limit as the limit h tends to 0, and here we have 2 times greatest integer of minus half minus h, that is equal to minus 1. So here we have minus 1, then we have here minus 3 by 2 and minus 3h, and here we have minus and greatest integer of minus half minus h, that is minus 1. So this is limit h tends to 0. This is minus 2 and minus 3 by 2 minus 3h plus 1. So taking limit h tends to 0, this term is 0. We have minus 2 minus 3 by 2, and here we have minus 3 times 0 plus 1. So minus 2 minus 3 by 2 plus 1, and we can write minus 2 over minus half, and minus get cancelled. We have 2 times 2 over 1, that is 4. So the left hand limit is also equal to 4. So now let us find the value of the function at this point, that is minus half, right? So we have 2 times, here we have minus half, and then we have 3 times minus half, and here we have greatest integer of minus half. Now the greatest integer of minus half is greatest integer of 0.5, and the value of greatest integer of minus 0.5, due to the definition of greatest integer function is minus 1. So we have here 2 times minus 1, then here we have minus 3 by 2 minus minus 1. So this is minus 2 minus 3 by 2 plus 1 minus 2 minus 3 plus 2 over 2. So minus 2 over minus 1 over 2. So this is 2 times 2 over 1, that is 4. So the value of the function at this point, that is x is equal to minus half, is also equal to 4. So, viewers, from this discussion, we have arrived at the conclusion that the right hand limit is equal to left hand limit is equal to f of minus half, because the value of these three quantities is equal to 4, right? And we can claim, due to the definition of continuity of functions, a function is said to be continuous at some point, say x is equal to a, if the right hand limit, that is limit x tends to a positive, f of x is equal to limit x tends to a negative, f of x, that is equal to the value of the function at x is equal to a. So here we have taken the function as y is equal to f of x. So viewers, this function f of x is continuous at x is equal to minus half, because the right hand limit and the left hand limit along with the value of the function at x is equal to minus half, all these three quantities are equal to each other, right? So this function f of x, it satisfies the definition of continuity of function, which says that a function is said to be continuous at some point, say x is equal to a, belonging to the domain of the function f of x, if the right hand limit is equal to the left hand limit is equal to the value of the function at the given point.